stuff open that we didn't need. There we go. All right, welcome back everyone. If you hear any loud noises or weird noises in my house right now, just ignore them, as I will do my best to as well. I am probably going to cut class about 10 minutes early today. I think I said that I've got some home construction stuff going on, and we're doing our best to avoid the teaching times, but you know, sometimes you can only do as much as possible. So let's get right into it. Let's pick up where we left off in 3.2. So just kind of very quickly, just showing the things that are part of the process. We have our leading coefficient test, which is how we tell whether the ends point up, down, or some combination, all based on whether your exponents, your leading term's exponent is even or odd, and whether its leading coefficient is positive or negative. And we said that that related to the graphs of x squared and x cubed. Then we talked about the behavior at a 0 or at an x-intercept, and how the multiplicity being even or odd, in other words, the exponent of the 0, tells you whether you bounce or cross on the axis at that point. Some examples of bouncing and crossing here, and how they relate to x squared and x cubed. And we determined some behaviors, and then we finally discussed turning points, gave you an ultimate process of graphing pretty much any polynomial. Now, we will have some complications of polynomials that we haven't seen yet, and that'll be once we get to, I think, 3.4. But this is still the ultimate technique list. It's just that sometimes finding the zeros is more complicated than factoring or quadratic formula. So that's something that's going to come up later. This finding the x-intercepts might be a little more complicated than what we've seen so far. But we'll save that for another day. We did one example. We sketched this graph. We did all of those different steps of using the leading coefficient test to say what the ends do, then finding the x-intercepts by setting the function equal to 0. That substitution technique came back up. We said that some of you may be able to go straight to the x squared minus 1, x squared minus 1, and that's just, you know, if you can, then that's fine. If you need to show the red version of it to get there, that's fine as well. We said this one had some weirdness with the factoring because these were both factorable, and when these are both factorable, you don't want to squish them together, so we broke it down and then squished the common parts together just to make finding the zeros and the multiplicities a little easier. We found the y-intercept, which gave us 3 points in total. We plotted those 3 points. We, in red, showed the end behavior. We came from the left, and then just bounced here, and just kind of hit all those points along the way. You're not going to be trying to hit the points in straight lines. You want them to be smooth curves, as smooth as possible. Buttery smooth, silky smooth, however you want to say it. All right, where did my page go for B? Here we go. All right, B. We're going to sketch still, and this is going to be f of x equals x plus 3 squared times x minus 5 times x plus 4 squared. So starting out, this function looks different than the last one because this is in factored form, whereas the other one was not. The reason I've given you this one in a pre-factored form is because if I gave you it in the expanded form, you'd probably get a headache almost instantly trying to factor it. It's achievable via the technique we'll pick up in 3.4, but for now we're not ready, so we're giving it to you already factored. That would also make it a problem that's about twice as long roughly, so we don't want to have that gigantic problem if we don't have to. All right, so first thing we do is we talk about our end behavior, which is where we just look at the leading term, but we don't see the leading term because it's factored. This is where we said, just pretend like all the plus and minus numbers inside the parentheses aren't there, and that's your leading term. So there's no number and a sign outside, so it's a positive. X squared times x squared would be x to the 5th. So the end behavior is that your function goes like positive x to the 5th. So that's an odd exponent and a positive coefficient, which means that while you don't know what happens in the middle, we know that the right side will go up and the left side's going to go down. So that's going to be very important for establishing the start of the function, because we know where to approach from, the top left or the bottom left, and where we should ultimately end up after we plot our points, bounce, cross, whatever's necessary. All right, next up in that list, which you should have written down, I certainly hope, your x-intercepts, and this is where we set the function equal to 0. So this will be 0 equals x plus 3 squared times x minus 5 times x plus 4 squared. Let's zoom in just a little. This is already factored, so we can go ahead and use our 0 product rule. We're going to set our x plus 3 squared equal to 0. And some people will just go ahead and ignore the exponents here. That's fine as well. You can't ignore them completely. I just mean for the solving process, because the exponents tell you the multiplicities. Then we have the x minus 5 equals 0. And then we have the x plus 4 squared equals 0. But when you take plus or minus square roots of 0, it's 0. So this just becomes x plus 3 equals 0 and x plus 4 equals 0 for the first and third one. You'll subtract 3 on both sides to give you negative 3. You'll add 5 on both sides of the middle one to give us positive 5. And then we'll subtract 4 on both sides for the last one and get negative 4. So those are the x values of the x-intercepts. This is where we'll be crossing or bouncing on the x-axis. But we need to establish whether we're bouncing or crossing. And that's a lot easier than doing something like f of negative 3.1 and f of negative 2.9. That would ultimately determine if it bounced or crossed as well. But you're plugging in decimals, the math is going to be uglier, and it's just not as methodical. This is a much more efficient method. So our multiplicity, again, based on the exponents, was 2 for the first one, which is even. It was 1 for the middle one, which is odd. And then it's 2 for the last one, which is, again, even. It's not whether the intercept itself is even or odd. See, this negative 3 is an odd number, but it's an even multiplicity. Evens bounce, and odds cross. If you were taking a test and you got to flip a coin to get that, to say whether they're bouncing or crossing, that's pretty terrifying because you got a 50% chance of getting it wrong. Please try and remember why they bounce or cross. And that's why I like the x squared and the x cubed graphs, because x squared you see a bounce, and then x cubed you see a cross. Picture's worth 1,000 words. All right, so there's our x-intercepts. Let me just squeeze in the y-intercepts over here, or intercept, excuse me. They're always singular for functions. And that's when we're finding f of 0. So f of 0 is going to be 0 plus 3 squared times 0 minus 5 times 0 plus 4 squared. So f of 0 is equal to, that's 3 squared times negative 5 times 4 squared. I didn't need the parentheses for that last one, but that's okay. 3 squared is 9, so that's 9 times negative 5 times 4 squared is 16. And I know no one wants to do that in their head, even though it's not the end of the world. 9 times 5 is 45. I forgot my negative, but I'll just negate it at the end. Times 16 is going to be negative 720. Again, I did not type the negative for the 5. Please don't be mad at me for that. So we know this is negative 720. So between the intercepts, the x-intercepts and the y-intercept, we have 4 points. We have negative 3, 0. We have 5, 0. We have negative 4, 0. And we have a pretty ridiculous one, 0, negative 720. Sorry, I had to squish that 720 in there. End behavior, x-intercepts, y-intercepts. We might be able to argue about symmetry, and I think I pointed out that the last graph we did, this did have symmetry. We could have only plotted the right half and then mirrored it across the y-axis, and that's because this original function does turn out to be even. If you plugged in negative x, you would get the same thing as f of positive x. But again, we didn't have to do that. Yes, it can be helpful sometimes, but it's usually not mandatory. It's generally not mandatory. Now maybe this one has symmetry, maybe it doesn't. I have a very difficult time just looking at this function and trying to tell. I would need to expand it to be able to tell that. And I don't expect it to have symmetry, but again, I usually don't test it if I don't feel the need. And I don't feel the need here. So hopefully that's going to be enough to get our graph. Let's see if these points, the end behavior, and then just some nice smooth finishing along the way can get everything together. All right, so let's do a nice big, oops, set of axes here. I thought I hit black. Oh, I know why. I know why it did that. And I had a pretty ridiculously large y value in the negative side of things, so I'm going to need a lot of negative y-axis exposed. I don't really need a lot of x-axis, so this will be okay. We're just going to do something like this. All right, so -3, 0, so I need to go left 3. 1, 2, 3. There's -3, 0. Then we have 5, 0, so from the origin we go right. 1, 2, 3, 4, 5. There's our second point. Then we have -4, 0, so from the origin left 4. You can label all the numbers if you like. 0, -720. Obviously, I'm not going to hash mark off 720 notches. I'm just going to say somewhere all the way down here, here's -720. That looks like 700. And there's our fourth point. I can mark our end behavior, which again, I don't want to put the end behavior inside the graph like that. I just want to kind of have it on the outside of it. These are reminders. These are footnotes, if you will. So we said since this went like a positive x to the 5th, the left goes down and the right goes up. This is all we need to sketch our polynomial. We're not going to make a perfect graph. There are going to be some minor issues along the way that we could certainly address by finding f of 0, f of 1, f of 2, f of 3, f of 4, f of 7, f of whatever. But that's not the point of this. So let's get our sketch. We're supposed to be coming from the bottom left. Now you might think, well, let me kind of come in like this so I eventually hit that point. That's a little too flat in my opinion. When we have these larger order polynomials, x to the 4ths, x to the 5ths, x to the 6ths, they're pretty steep usually as you go far out. So I think it's probably going to look something like that, and even that might be a little too bendy, but it's good enough for government work. So something like that. And you know what, since I've got this point over there, I want to come all the way down here. Doing my best. All right, there we go. Now at that -4, what did we say? Is it going to bounce or cross? The -4. Here's the -4, and we said it's going to bounce. So it's going to turn around. It is not going to do this. That would be wrong. It's bouncing, so it's like the x-axis is a ceiling. So it turns around. I'm going to zoom in a little. Now, okay, we turned around, and you might think, okay, we'll keep on trucking. But unfortunately, we got to hit this point, which means it's actually going to have to turn around pretty quickly. So it turns around, it bends like this, but eventually it's got to turn back around so that they can hit that point. And it's probably going to have a nice little peak halfway between the -4 and -3, but we don't know exactly how low it's going to be. It might be something like this, or it could be really extreme, and it might be something like that, or it could be even more extreme, and I did not do that very well. This is going to be tough for me. I don't know that I can really go any further than that. Now, do I think that that's going to happen? Probably not, because like I said, we usually have these nice, smooth, transitional movements, and there's not a lot of space to smoothly transition that ridiculously low. So my best hunch is that it looks something like this. Now, doing this by hand on a test, if someone else thought it was going to do this, I'm not going to take any points off from them, because you're guessing. The only way you could figure that out is if you did f of -3.5, which you're allowed calculators. You can certainly do that. I have no problem with that. But again, you can still do all of this stuff without a calculator, so you're just kind of guessing. In order to figure out exactly where this point is, you actually need calculus, and I'm not going to teach you that in here. it's not as easy as the limit of f of x plus h turning into that whole f of x plus h thing. So that's my best guess for this. So we said we bounced here. Now the question is at -3, what do we do? Well, at -3, we also bounce. And then at the +5, we'll cross, so I don't have to scroll up again. So at the -3, we're supposed to bounce. So we don't go up, we come back down. Now you go, okay, well, eventually we've got to hit this point. So there's something that says eventually we're going to come back up here. Now, just looking at what we have on the screen right now, nothing says that that's wrong, but unfortunately, I don't have everything on the screen because we did calculate the y-intercept, and it was that ridiculously small -720. Small because negative. So we got to come all the way down here, hit that point, and then we got to come back and hit this 5. Now, I've suggested to you that if you have two intercepts, the peak or valley between them is usually halfway between them. This point is not halfway between -3 and 5. It's a little to the left of it, right here at +1. That would be halfway between -3 and 5. So if I had the point at f of 1, I'd be more inclined to think that that was the lowest point. My point being, I do not expect this to be what the graph does. What I'm doing right here is not what I actually expect. However, if a student did this, once again, on a test, I would not mark this wrong. If this was your paper version of your work, which I do expect to see handwritten graphs on this test, another case of I reserve the right to not award you any credit if all you did was just pick a multiple choice graph. I need to see the work. That's what I care about. So again, this is not right. Again, because the halfway point's at 1, this is probably not the lowest. Notice I said probably. There's some weird functions out there that it could be. So I expect the halfway point to be probably around where the 1 is, and even that doesn't have to be exact. So it probably does something like this. It probably hits that -720, goes down a little more, and then eventually turns around. Now, how low that turnaround point is, doesn't matter. Again, I'm just kind of guessing. And then eventually we hit the 5. And then we said at the +5, it crossed. At x = 5, it crosses. So we do not do this. We do not turn around again. You might say, well, we turned around twice, so let's do it again. No, that would be wrong. It crosses there, so we keep going up. Now, there are no more x-intercepts. If there was a point here, I'd have to turn around and hit it. But we found all the x-intercepts, which means this thing is forced to keep going up. It's possible, it is possible in some world that it might have a couple extra turning points in that process to keep going up, but we don't make that assumption. We do not make that assumption. We like to assume the simplest case possible, and it matches the end behavior. So that's a good sign. And remember that we said you can count the turning points. 1, 2, 3, 4. There are 4 turning points. And we said the number of turning points can be at most 1 less than the degree. The degree of this polynomial was 5, which means this is the absolute maximum number of turning points. It is not possible for the graph to have done this because then you'd have 6 turning points, and that would be too many. So here, let's pull back. And of course you want an arrow on the left side as well. Here is our graph done as best as we humanly can as pre-calculus students without a calculator on ourselves. Now what we can do is we can pull out a calculator and go, well, how good does this look? So we can type that function in to our calculator, which I said you are allowed to use calculators on this upcoming test, but they're more meant to be checks and balances versus how do I do something. So I'm only using this to confirm the appearance of the graph. I'm not supposed to be using it to do all my work, which is why I am extremely stressing that you have to show your work for this stuff. I'm going to grade the work more than the question on my math lab. I will be going back and looking, hey, did the student do their work or did they just type everything in a TI-83? If I don't see any work, you're not going to get any points. Because this TI-83 has ways of telling you every single detail up here. All right, parentheses, x plus 3 squared. Then another one, x minus 5. Then another one, x plus 4 squared. Let's check and make sure that's right. X plus 3 squared, x minus 5, x plus 4 squared. We hit graph. And quite honestly, we're not going to see everything. We see a lot of what we had up there. Let's scroll down. So we can see, let's do this. There we go. We can see this detail. Now, look at that. I have red pen on and it did blue. Please tell me that doesn't make sense. Okay. So we can see this section, which is right here. We can see this section, but we don't see anything down here because this window is stopping at -10. So what I can do is I can go to the window. I'm going to mute for a second. And I don't think I muted in time. And we can just change these y mins and y maxes. Now I know I've got this -720, so that y minimum needs to be at least that much. Let me make it -1000 because maybe I'll get to see where that valley is. I wonder if y'all can hear that. So even it going as low as -1000, I still can't see the bottom. Now, I don't see as much detail anymore. I don't see these humps right here. It looks like it's just doing this, but that's because I have really pulled out on the y-axis. So that detail is missing visually, but I can see, oh yeah, this thing really is going down to that ridiculous -720. I can even hit trace, and if I type 0, actually I didn't have to, I can see that that point is -720. So let me change my window again. Let me go to maybe 5000. That ought to do it, I hope. So again, the detail is lost up here, but now I can see where this point is. And what I can use my calculator is I can hit trace, and I can just go over and get an approximation to that point. So it's in the ballpark of 3.5, and it's about -3600 roughly. Again, I can't get that exactly. There are ways to get it in the calculator, but I'm not going to talk about that because I don't care for a pre-calc student. Calc, I would. So again, that point really should have just, this graph should have gone more like this, but I'm not going to take any credit off of myself for that. I'm not going to take any credit off of your graph for that on a test. Because this is an excellent approximation without using any technology at all, and that's the ultimate point of this. All right, so I'm looking for something that I can't seem to find. I have another page of problems. I don't know where it went. Nope, not that one. I'll make one up on the spot if I have to. Here it is. Boom, got it. All right. So again, I know this is an arduous process. I know that we're making a lot of guesses, like we guessed here, we guessed here. We made kind of a bad guess here, but again, in terms of sketching, this is good enough. This, we ended up making a pretty good guess. If we go back to a normal zoom, if I just go back to -10, we can see that we made a pretty good guess there. And in fact, I would say this is even, considering that this is -720 down here, it probably should have been like that. But again, for a sketch, it is more than good enough. Now, what you can do is when you pull your calculator out, you can go, oh, okay, well, that was tiny, so let me erase this and just kind of edit it. And you go, oh, well, this should have been steeper, so let me erase that section and make it much, much, much steeper than that. So that's what the technology is there for, not to tell you, oh, I can see my X-intercepts, I can see the left going down and the right going up. That's not what it's there for. I need the work, no credit. I know that sounds mean, but that's the point of this course. All right, one more of these, and then we'll get into the next section. f of x equals x to the fourth minus 9x squared. Same process, we're going to do the end behavior, we're going to do both types of intercepts. I'll point out if it's symmetric or not, which obviously the one we just did is not symmetric. Now, first of all, in my head, I only see even exponents, so that's a clue that it's probably an even function. Again, a constant up here can throw things off. Maybe that means it's even, maybe it means it could have been odd instead. It wouldn't be odd because of the even exponents, but just know that constants can throw things off, so you should still remember how to do that official test. Plugging in f of negative x and seeing that you get the same thing makes it even. If you do that as well as negative f of x and they're the same thing, that means it's odd. All right, so this is not in a factored form, so we can go ahead and talk about the end behavior. We're just looking at the leading term, so f of x goes like x to the fourth for really large values, which is an even exponent and a positive coefficient, which means that while we have no clue for now what happens in the middle section, the left should go up and the right should go up, because that relates to the positive x squared graph. Then we can do our x-intercepts, which is setting the function equal to 0. That is not a 0 inside. I know I wrote that first. I didn't mean to. F of x equals 0. F of 0 being 0 is something entirely different. All right, so we go 0 equals, let me zoom back in a little, not that much, x to the fourth minus 9x squared. There's a GCF here, we're factoring, which is x squared. So we go 0 equals x squared parentheses, then x squared minus 9. X squared minus 9 is a difference of squares, so we go 0 equals x squared times x plus 3 times x minus 3. And then we zero product rule this. So we go x squared equals 0. Am I going to have enough room? It'll be good enough. X plus 3 equals 0, and x minus 3 equals 0. I'll just use the page below. I've done that before. X squared equals 0, you take your plus or minus, square root of both sides, and you get x equals 0. We've already talked about that many times and how the exponent is irrelevant. For that, it's relevant for the multiplicity, but not the 0 itself. Subtract 3 on both sides, you get x equals negative 3. Add 3 on both sides, you get x equals positive 3. For our multiplicities, it's 2 for the first one, 1 for the middle, and 1 for the last. Because there were no exponents seen, that means they're implied to be 1s. That's even, so it bounces for the first one. These are both odd, so they both cross for the middle and third. Now when I say middle and third, I don't mean necessarily left or right on the graph, just in this order right here. Then we can do our y-intercepts. Intercept, I keep saying an s at the end and I don't mean to, which is f of 0. Which is 0 to the fourth minus 9 times 0 squared, which is 0. So we have points of, with x equals 0, that says an x-intercept is 0, 0. Then we have the negative 3, 0. Then we have the 3, 0. And then we have inflection in voice. The y-intercept f of 0 was 0, which means that point is 0, 0. Which is the same as the x-intercept we found earlier. So the y-intercept is the same point as one of the x-intercepts. That can happen. We've seen that happen previously in this course, and it's because the x and the y-intercept are both the origin. So I only got 3 points, even though I did in this extra process, I didn't pick up an extra point, it was just a repeated point. And anytime you go through the origin, you better pick that up through the x-intercept process and the y-intercept process. It'll always happen. We know, let me actually write whether they bounce or cross here. The one at 0 bounced, the others crossed. Okay, we got our end behavior, both ends went up. There's no ridiculous values of points this time, so I can scale my axes pretty evenly. So negative 3, 1, 2, 3. Positive 3, 1, 2, 3. And then our points are negative 3 comma 0, 0 comma 0, and 3 comma 0. We know the end behavior, we said both ends are going to point up. I just kind of put them way out to the side, so they're not part of the graph, it's more of a footnote. And that is literally all we need. Again, yes, one of those steps was test for symmetry if you want to. You don't have to. And I pointed out that because we only saw even exponents, that I do expect that this function is even, and it does turn out to be even. I'll show you that at the end after the graph, but I'm going to show you us doing the graph without it to prove that it's unnecessary. All right, so we're going to come from the top left section. We don't want to approach from all the way over here because then we're kind of coming in too flat. Again, they're usually pretty, you have a pretty good steepness to them, something like this maybe. And then maybe we bounce across. Well, we said at the negative 3 we're supposed to cross. So we are supposed to go through. Now, maybe we're going all the way down here. Maybe we're more flat. That's not something I expect you to anticipate. I actually want to start this over. So, Now you might say, well, do we just go down forever like this? No, we got to hit this point. We're thinking about the next points that we have to hit along the way. So because this point is above it, at some point I have to turn around. And again, I'm not expecting you to know how low that turnaround is, so we just kind of guess. And by guess, I mean make it look pretty usually. Then at this point, at the origin, we were supposed to bounce, so we do not do this. That would be wrong. We have to bounce, so it's going to do something like this. Then we're supposed to hit this point next, which means we're going to have to turn around at some point. We'll have to bottom out. So we'll cruise down for a while. Now, it is certainly possible that it looks like this, that these aren't exactly the same height, but I like to assume simple is usually what happens. So I'm going to mirror it and then hit that positive 3. And then at the positive 3, we're supposed to cross. So don't turn back around and go down. Keep on trucking up. There's no other points that we have to hit, which means I don't have to turn around anymore. It is certainly possible that this thing wiggles 500 million times if the polynomial had an exponent of 10 or 20 or 30, but it didn't. The polynomial had a leading exponent of 4, which means there are at most 3 turning points. And I see 1, 2, 3, so I definitely can't even do this or this. I just have to keep going up. Up, 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 up. We put arrows on the ends, and I feel pretty confident about that. I'm feeling pretty good about that. And the image I drew ends up looking symmetric. And you might go, well, Mr. Beckner, you assumed that this hump had the same depth as this one over here. And I said, you generally prefer to assume simple cases as you're kind of going with this. But remember, you can use your technology to back you up on that. So let's clear the old one. This was x to the 4th minus 9x squared, I believe. Minus 9, don't forget the 9. Let's double check that. X to the 4th minus 9x squared looks good, graph. So our picture looks pretty good in terms of, hey, this looks good, this looks good, this looks good. We're touching here, we're touching here. The only thing I think that doesn't look perfect is, and I tried to allude to this earlier, should probably be a lot lower than I have it represented, but at the same time, I also haven't labeled any y values yet. See, I could just call this value right here, maybe negative 50, and then boom, all of a sudden it works. So if you wanted to know how low those values are, you can just pull the window out. Maybe let's go to negative 50. I don't know why I have a hunch that it's around 50. Okay, so I overshot it, but it's definitely in that span. I can hit trace and okay, it's around 20, negative 20. So instead of writing that as a negative 50, I can just go that it's about negative 20. And again, I don't have to do this by hand. I don't need that detail because there were no other numbers on the y-axis. Again, just this, even though you're probably thinking that this is about 3 since this was 3. Some people might go, well, that doesn't look great. It should be a lot steeper. But I can just say I'm not scaled on the same distance in the x position as the y position. So you don't have to do that. This is perfect right here. If I said that this was -3, then I'm going to go, well, you shouldn't have put that -3 up there because that height's not really correct. Am I going to take any points from you? I don't know. A half a point maybe at worst. 1 point at worst, but everything else is beautiful and wonderful, so I don't even know that I would want to. I would just say, don't put the number up there. Remember what your teacher said. That's the best thing you can do for yourself. All right, so that was pretty good. Not too bad at all. So this is what I expect in terms of test questions. This is the ability I expect you to have, not to make perfect images. This one right here, we were able to figure out how high that was because it just happened to be the Y-intercept. It was a nice coincidence. We don't always get those coincidences, and then we have to play guessing games. And guessing games are fine as long as you know what you can play a guessing game on. You're not guessing that this is a bounce and that this is a bounce and this is a cross. That's not a guess. We gave you techniques for that that don't involve technology. Right. So that is 3.2. Sorry, I'm looking at something real quick just to make sure I didn't miss anything. I have a couple pages that aren't exactly in the right order. So that's why this throws me off in this chapter. And it's only this chapter. I don't know why I did it that way. I usually go front to back, and for some reason, this one I didn't. Okay, we're good, we're good, we're good. We're good. Okay, so that's 3.1 and 3.2 completed. So 3.2 will be due in 1 week. So today's the 11th, so 3.2 will be due on the 18th, just so you know. Again, 3.2, due 11, 18. Now we're into 3.3. So 3.3 is all about dividing polynomials. We're going to give you 2 different techniques for dividing polynomials. We're going to give you the traditional division method, which is something that you should have seen in one of your prerequisite classes in Algebra 2 or in MDE, as we call it now, or Math 5 through 9. We cover that long division. However, I am going to give you the full method in here. We will do a couple examples, 3 examples to be specific. And then I'm going to tell you that we're never going to do long division again in this course. I'm not saying that long division isn't a good technique. I'm saying we'll never do it again in this course. I will throw 1 question on the test, maybe even on the final, but it's not going to pop up in later sections of Chapter 3. It's not going to pop up at all in Chapter 4. It's a good technique, but for the thing that we are building to, we are going to, instead of doing this traditional long division technique, we're going to do synthetic division, which some of you may have seen, some of you may not have seen, and if you haven't, then you're in for a ride. But synthetic, synthetic is kind of like a hybrid, a fake thing. It's a way of taking out a lot of the middleman work of long division, where these problems will take up half of a page vertically and probably take you 10 or 15 minutes to do. We're going to trim the fat out of it completely. We're going to take away all the x's. We're just going to put a few numbers up. We're going to do really quick multiplications and additions, and then the whole thing's going to be done in like 30 seconds versus taking 10 or 15 minutes. So again, we are only introducing the long division technique in here for the appreciation of synthetic division, because what we're going to end up doing in the next section is literally dozens and dozens and dozens and dozens of synthetic divisions. And problems won't just be, hey, do synthetic division on this. It'll be, hey, you need to find all the zeros and you need to know to do this synthetic division to find them. And you might be thinking, well, Y-Dash factor. Well, I was talking about earlier how the factoring and quadratic formula are going to stop working all the time. We're not going to know these advanced factoring techniques. All right, rant aside, let's get it. Long division with any binomial or more denominator. So when I say binomial, I mean we don't care what the top is. It's just the bottom is going to be something like x squared plus 3x minus 5. That would be a trinomial. Or x minus 7 or 3x plus 17. I'm just saying that the bottom's got more than one term. This would be a monomial, which if you have a monomial, you just split the fraction and reduce each fraction. That's an old technique. So that's what we're talking about, fractions with more than one term in the bottom. So here's the way you're going to do things. You're going to first divide the leading terms. So you're going to have a whole bunch of terms in the top. You'll have at least 2 terms in the bottom. The first step, you're going to ignore everything except the first term in the top and the bottom. And it kind of is like when you do regular long division of numbers and you only look at the first couple digits or the first digit depending on how you're doing things. This technique mirrors long division of numbers exactly. It just feels more complicated because we're dealing with x squareds, x cubes, and x to the fourth, things like that. So in long division of numbers, the process always goes divide, then multiply, and then subtract. And you keep doing that until there's nothing to bring down. Divide, multiply, subtract. Literally the same thing. So divide the leading terms, you'll put the answer on the bottom. Then you will multiply whatever you just got by all the terms on the left. By all the terms on the left. So when you do the division, you're only looking at leading term and leading term. When you do the multiplication, you're taking your result and multiplying it by all the terms on the left. Then for the third step, what you do is, and I have it in quotes for a reason, you're going to subtract. So normally, let's say you had, I don't know, 5 going into 73. You'd say 5 goes into 7 once. That's the division. 1 times 5 is 5. That's the multiplication. And then you subtract. 7 minus 5 is 2. Then you bring down the next number, which is bring down the next terms. But I have it in quotes because these are not going to be numbers. They're going to be variables. And there might be a variable here and a variable here and a variable here. And that minus, you might not think to implicitly give it to all of them. So instead of just doing a traditional subtraction, we change all the terms on the bottom sign. So if it was positive, you make it negative. If it was negative, you make it positive. And then you just add vertically. You combine them vertically based on the new signs. So changing all the terms' signs is equivalent to subtracting because subtracting makes all signs flip. And then you just keep going until you can't go anymore. So that's our refresher on the long division technique. We're going to do 3 examples, and then as I said, you'll never see me do another one in this course. I'm not saying long division is a throwaway technique. It is absolutely critical for many other things in math, just not for this particular course. When you get to Calc 2, maybe even Calc 1, depending on where you take it, that long division issue will come back up. I don't even want to talk about what it is, but it does come back up. So don't think that you get to forget this, but you know, it might be another year before you do it. So just understand that you'll have to de-rust again if you do forget it. Okay, so let's get it. I just don't want this still up there. And then notice that I have a super special 3 asterisk memo. If any terms are missing from the numerator, you're going to need a 0 in its place. This is kind of like if I had the number 5009 and I wanted to divide this by, say, 11. I can't just say 11 into 59. That's not the same thing. The zeros are placeholders for the tens and the hundreds. I have to go 11 into 5009. Terms missing is like having a digit missing. So you need a 0x squared, a 0x cubed, a 0x, if any of those things are missing. You might say, well, how far do I need to go? Well, whatever the largest one you have is, that's how far you need to go. It's not too complicated. That issue will be seen in notes, homework, maybe even test. All right. Example 1. Simplify by long division. A, we got x squared plus 3x minus 10 divided by x minus 2. How are we on time? Okay. So this is a rational. And some of you might be thinking, oh, Mr. Beckner, with rationals, didn't you say to factor and reduce? Why, yes, I did. But guess what? Not all rationals can be factored and can reduce. So sometimes we have reasons to want to simplify this, to reduce it, to divide it, whatever you want to say. But you go, oh, well, it doesn't factor, so I can't just do that. Or when I factor it, nothing cancels, so that doesn't help. So you'd be forced into this technique. Now, I'm not saying this problem is forced in the technique. Let's try it out. We'll talk about that after the fact. All right, so the bottom is what goes on the left. X minus 2 goes on the left. The top is what goes on the right. X squared, X, and 10, we're not missing anything. And also make sure that they are in that order. Make sure they're in descending order. They have to be in descending order, because this is kind of like our hundreds place, our tens place, and our ones place. Anything in the wrong place, if you put your tens in the thousands, you're going to have a bad time. All right, let's pull back the instructions. Divide the leading terms. So when I say leading terms, I mean this and this. Now, some people like to go to the side and show their work for that. So I'm going to divide the x into the x squared, which is literally just doing x squared on top of x. That is me dividing the leading terms, which we can reduce to a power of x to the first. So that's what goes in the top. You don't put it here, you don't put it here. You want to stack them appropriately. Here's your x column, here's your quote tens, if you will. So that's where your x should go. Then we're on step 2. Multiply this result by everything on the left. So the x times the x is going to be x squared. Then the x times the negative 2 is going to be a negative 2x. Now, before I continue, I'm going to do something very unusual that I suggest you do as well. And here's the reason. Step 3, you're going to change all the signs. I don't want to erase the previous signs. I want to just put them above and say, use the top one. It's not going to mean if you see a plus minus, it means both things are happening. It's the bottom was what you got originally. The top is what we'll use for the next step. I don't see the original sign for this one. So even though it's positive, even though I know it's positive, I'm going to write a positive for the sole reason because I'm going to change that sign, and I don't want to get confused looking at my notes a week, a month, or 6 months or a year later. So that way when you see both, you'll go, oh, that's right, it was originally positive and now it's negative. So then you change the sign, change all terms on the bottom signs. You're not changing anything here or here, you're just changing what I have in red. So this becomes a negative x squared and a positive 2x. All negatives become positives, positives become negatives. And then you just combine vertically. See, if I didn't have this plus here originally, I'm going to think when I look at my notes 3 months or 6 months from now, I originally said that x times x was negative x squared, and I'm going to go, what the heck was I thinking? It's positive x, and then I might change my notes, and then I'm really messing things up. So that's why I say, do something a little different and put that plus there, even though you might not want to. All right, so x squared minus x squared cancels, it makes 0. Spoilers, that's always going to happen. The first one should always cancel. If it doesn't, I can guarantee you made a mistake. Then the 3x plus the 2x is a 5x. See, I'm using the top ones, the changed signs, and then we just bring the minus 10 down. You can bring everything down if you feel the need. You can bring just the next term down. There are problems where you'll have to bring more than one term down, but I don't even know that I give you any in homework or test. Definitely not the test, and I don't think they're in the homework. And then you just, as your Spanish teacher would say, repita por favor. Do it again. Go back to the first step, divide, multiply, and subtract. Now, divide the leading terms, we're not looking up here anymore, we're looking down here for the division. So what's left over is the 5x minus the 10. So we're dividing the x into the 5x. I hit undo too many times, didn't I? There we go. All right. So again, I'm just going to do that division to the side. So we get 5x over x. The x's will cancel each other out, and that gives us 5. Now, I definitely can't just put a 5 here. That looks like x times 5. So this is another case of you really need that sign there. It would be awful without that sign. You can still understand things if you're really good without this plus sign down here. That one is mandatory for sure. Multiply this result, just the 5, not the x in front of it, just the 5, by everything on the left. It's like we're distributing it. So the 5 times the x is a 5x, but I said, I know I need to write this plus because it's going to change, and this 5 times this negative 2 is a negative 10. then we change the signs of what we just got. The positive 5x becomes negative, the negative 10 becomes positive. You're going to notice a coincidence in my problems that I do a lot of plus minuses becoming minus pluses. That's mere coincidence. They could all be pluses turning to minuses. They can all be minuses turning to pluses. It doesn't matter. Combine 5x minus 5x, cancel. Again, that should happen. Negative 10 plus 10. Oh, they actually cancel. But I got to write something down here, so I need to write a 0. There's nothing else to bring down, so that means we're done. And when we're done, whatever is here is what we call the remainder. The x plus 5 is what we call the quotient. Now, as a reminder, when you do long division, your answers, whoa, sorry, I had a little too much fun there. Your answer goes quotient plus remainder over the original denominator. Notice that it's only the remainder over the original denominator. The quotient, we divide it out. We call the remainder because it's what remains to be divided. The quotient has done the division, so no more fraction. The remainder remains to be divided in theory, but we can't handle it, so we leave it that way. So there's our quotient, there's our remainder. Our original denominator was x minus 2. So at the end of the day, what we get is the x plus 5, there's our quotient, then plus the remainder of 0 over the original denominator of x minus 2. Is anyone scratching their head a little? I sure hope so. Do you really need to write 0 over x minus 2? No, 0 divided by anything is 0, so that's just x plus 5. That is our answer. What this means is this problem divided perfectly. What this means is the original problem was factorable and it would reduce. So as I pointed out before I started this problem, a lot of students would go, oh, a rational, factor and reduce it. But I said not every rational factors and reduces. That's the whole point of long division, a way to kind of split things up if they don't factor or if they do factor and they don't reduce. So just note, a clever student could have just said, oh, well, the top is factorable, factor pairs of 10 that subtract a 3 or 2 and 5, so we go x2, x5. To make sure they subtract to a positive 3, the larger needs to be positive, so minus 2 and positive 5 over x minus 2, and then they'll go, oh, hey, same thing top and bottom, they cancel, and boom, x plus 5. Same answer. They finished it in like 2% of the time that the long division process took. Now, I did say to use a specific method, so that means I could reserve the right to not award full credit if this was a test question. However, I will admit a long division problem that does factor and reduce, I wouldn't care if you notice that. I would actually commend you for it. Now, this remainder being 0 is what made this section not be here, so that it was just a quotient. There was no fraction left over, and that's what made it factorable. That's a very important concept that we're going to use moving forward. We're going to ultimately want to get remainders of zeros, but we're not going to be told what divisions to do. We have to decide what divisions to do, where the goal is to get a 0 remainder so that this happens, so that this happens. That's the point in 3.4. All right. B. Let's go with 12x squared plus x minus 4, all divided by 3x minus 2. So, our bottom is 3x minus 2. That goes on the left. Everything is in order. Everything is accounted for. There are no missing terms. We will see one that is missing terms eventually, though. Don't worry. And I already told you there's going to be 3 problems, so you know which one it'll be. And then the 12x squared plus x minus 4. I'm going to go a little quicker through this one. So divide. Can I fit all that there? It's going to be a tight fit. I can make it fit. I can make it fit. So divide just the leading terms, the 3x into the 12x squared. Again, feel free to show that work on the side. This is what we're doing. 12 divided by 3 is 4. X squared divided by x is a single x. That should go in the x column, not the x squared column. Neatness is important. Your teacher says hypocritically with horrible handwriting, but at least I am organized. 4x times 3x is 12x squared, but that's positive and we know we're going to need it. 4x times negative 2 is negative 8x. We draw our little line, and then we change these signs. I actually like to say draw the line, switch the signs. It's just a little motto that helps me remember what to do. The first terms will cancel as they should. So that'll be a 0x squared. The x plus the 8x is a 9x. We bring down the minus 4. Now we're going to divide again. The 3x and the 9x. So we get 9x divided by 3x, which is 3. I cannot just put a 3 here. I got to put the plus there. That's mandatory. Then we take this 3 and I did not show that distribution very well. We're just multiplying it to those two things. 3 times 3x is 9x, but we want to write that as a positive. 3 times negative 2 is negative 6. You might be saying, why aren't you writing the blue one in positive? Because I'm not going to be changing any signs, so it's not necessary. It's not wrong to do that. Then we draw the line. We switch these signs, so these become a minus 9x and a plus 6. 9x minus 9x cancels. Negative 4 plus 6 is positive 2. There's nothing else to bring down, so that is our remainder. The 4x plus the 3 is the quotient. So that says our answer goes quotient plus remainder over the original bottom. So 4x plus 3. Now that's a positive 2. If that had been a minus, then I'd just go a minus after that, or plus negative. That would work too. But this is plus 2 over 3x minus 2. That is the answer. This answer is not as special as the previous one because the remainder was not 0, which means that even if this was factorable, it would not reduce. I'm not saying whether it's factorable or not. Doesn't look factorable to me. It's not factorable. I had to think about it for a second. But again, even if that top was factorable, nothing would cancel, which means in order to just arrange this in some other way, which I'm calling simplifying, or if you were just told to divide it out, this would be the answer. Now, knowing this 4x plus 3 and then this 2 over a fractional part, there is something that's helpful with this in more advanced pre-calculus and calculus. There's things we can do with a graph, knowing that this thing turns into this thing ultimately. But we'll save that for another day. All right. I think everything seems to be good enough to be able to keep working. You know what? I got 2 more. No, I only have 1 more. I can wrap this in like 6 or 7 minutes. Okay. 4x to the 4th. This will be our last one for the day. Plus 6x minus 4x squared divided by x minus 4. There's several issues with this one. First of all, the top is not in descending order. You got your x to the 4th here, your x squared here, and then your x here. So they're in a bad order. So someone might want to reorder them at least to 4x to the 4th minus 4x squared plus 6x over x minus 4. But on top of that, there is no x cubed term, and there's no constant, which means we're going to need zeros in their place because it's like we're missing the ones place and the thousands place. So when I write my actual division out, we're going to put the x minus 4 on the left still, but we're going to need those placeholders. So we'll have the 4x to the 4th. We know I don't need anything larger than x to the 4th. Then plus, and I'm going to do this in red for emphasis, 0x to the 3rd because it wasn't there, but we need that to have our placeholder. Then minus our 4x squared plus our 6x, and then that other placeholder of a constant 0 at the end. Again, without those, you are highly likely to make mistakes. It's like you're missing an entire digit of a number, You're going to start putting things above the x squared that might have been an x cubed, so that's going to be wrong. You're going to stack them below wrong. Lots of bad things are going to happen. All right, so let's get it. I'm going to need a little more room. There we go. So we're going to divide. I can squeeze this. Let's do the squeezing over here. So the 4x to the fourth and the x. So 4x to the fourth over the x would be 4x to the third, and that's going to go in the x cubed column, which we wouldn't have had without the placeholder. Then we multiply that by everything on the left. 4x cubed times x is 4x to the fourth, and that's positive. We know we'll need that sign. 4x cubed times negative 4 is negative 16x cubed. And then we're going to draw the line and switch the signs, because this is us subtracting. So the first ones will cancel as they should. Then 0 plus 16x cubed will be 16x cubed. See, like I said, a lot of students would have taken this term and put it under the 4x squared if that placeholder had not been there. And then you're going to combine things with different exponents, and you're breaking the law at that point. All right, bring the next term down. And this problem is going to be a little longer because we had a higher degree polynomial. All right, repita por favor. X into 16x to the third. So I'm doing my divisions over here. 16x cubed divided by x will be 16x squared. So that's a plus 16x squared. We're going to multiply that out. Oops, keep the red. 16x squared times x is 16x cubed, and it's positive. 16x squared times negative 4 is negative 64x squared. Draw the line, switch the signs. So that's negative, that's positive. Combine vertically, first cancel like they should. The second, negative 4 plus 64 is 60, and that's x squared. Bring down your plus 6x. Repita, por favor. So 60x squared divided by x will be a positive 60x. So we got to go plus 60x. We're going to multiply. That'll be 60x squared for the multiplying of the x. 60x times negative 4 is going to be negative 240x. But when we switch those signs, oops, I forgot to write my plus. I said it, but then I didn't write it. So that's a negative and that's a positive now. First pair will cancel. 6 plus 240 is 246x. Numbers are getting pretty big. That's okay. And then we bring the plus 0 down. Admittedly, this really won't affect us, but it's just a good habit. Then we divide the 246x divided by the x, which is 246. You can tell when you're done, or about done, because you'll have no more x's in your answers for the quotient. So plus 246, multiply, that'll be 246x, which is positive. 246 times 4, 250, that'd be 1,000. We're going to subtract 16, so 984. But it's going to be negative 984. Draw the line, switch the signs. Negative, positive. Add and you get positive 984. There's nothing else to bring down. Our quotient doesn't have any more x's, so we know that's the remainder. There's our quotient. So let me just scroll down here a little bit. Oh, come on, don't do that to me. There we go. So our ultimate answer is the quotient of 4x cubed plus 16. Ooh, that got ugly. 16x squared plus 60x plus 246, and then plus the remainder of 984 over the original denominator of x minus 4. There we are. So this one did not divide perfectly because the remainder was not 0, which means that top, even if it is factorable, it wouldn't have canceled with anything in the bottom, so it would have been a dead end. There's times in math where we prefer our problem to look like, or our whatever we're working with to be the original problem. There's times in math where we need to have it split up into some kind of quotient and remainders, like a polynomial and then a fraction scenario. And that's the thing about math. It's not always just one goal. It's kind of like factoring is the opposite of multiplying a polynomial out. Sometimes we want it factored, sometimes we want it multiplied out. You have to learn and understand things in both ways and know when they're necessary. All right, so I'm not going to leave this on the screen for more than a couple seconds, but this is what we're going to do next time. I am going to go ahead and call it a day so that my, let's call him construction assistant, or I won't say project leader would be much more appropriate, so he can make some noise before my next class. So we're going to go over synthetic division, which I've already alluded to. We can take all of these problems, which took us many minutes to do, and that was my time. For you, probably double or at least a few minutes longer. We're going to practice this technique so ridiculously much that we're going to be able to knock these problems out in like 30 seconds. Again, you see how much space this takes up. We're going to do this one again with synthetic division next class. It's going to take up about this much space right here. And that's going to be it. That'll be the whole problem, and we'll be able to rock it in 30 or 40 seconds, whereas this took 5-10 minutes. All right. So you know your homework expectations. 3.1, I think, is due on Monday. 3.2 is due next class. I might be wrong about that 3.1, but the due date's in my math lab, so whatever that said, whatever we said last class. Have a good weekend. Work hard. Email me with any questions. I know one or two of you have asked me about some test stuff. I haven't gotten to that, but I will, I promise, ASAP. All right, take care.